Hi, let's look at this final question. We're going to consider this function f of x equals 2x squared plus k plus 3x plus k. By finding the discriminant and expressing it in completed squared form, show that the equation f of x equals 0 has two distinct values for all values of k. Well, let's just set the f of x equal to 0 as it says first, because we're told that here. So we're going to say 2x squared plus k plus 3x plus k is equal to 0. And we want to show that this equation has two distinct solutions of x for all values of k. So remember, we can use the discriminant for that. If we have an equation ax squared plus bx plus c equals 0, if the discriminant is greater than 0, so this discriminant is this b squared minus 4ac here. If that discriminant is greater than 0, we have two distinct solutions. So that means for this equation, we want to basically be able to show that the b squared minus 4ac is greater than 0. So let's work out what our a is, the b is, and c is. The a is the coefficient of the x squared, the b is the coefficient of the x, and the c is the constant term. And we're then going to find the discriminant. So that's b squared minus 4ac. If we substitute into that, that's going to be equal to k plus 3 squared minus 4 times a times c. And let's just simplify that. That's going to give you k squared plus 6k plus 9 minus 8k. And let's just simplify that. That's k squared minus 2k plus 9. Now, it says we want to show that regardless of the value of k, for all values of k, that we have two distinct solutions. So basically, we want to show that this is always greater than 0 because the discriminant is always greater than 0 for all values of k. So how do we do that? So how do we show that this is always greater than 0? The discriminant is greater than 0. Well, for quadratic, we can complete the square. That's a good way to show that a quadratic expression is always positive, always greater than 0. So let's remind ourselves how we complete the square. You basically look at the coefficient of the middle term, the k term or the x term, and you halve it. So you're going to do k, and then you halve the minus 2 to get minus 1. And then you put squared, so you halve that. And then remember what you do is whatever we've got here, the minus 1, the halved term, we square it and throw it away. So we square and throw it away. So the minus 1 squared is 1. We throw away to get minus 1. And then if you were to expand this out, you get k squared minus 2k plus 1 minus 1. The plus 1, the minus 1 cancel, and you just get k squared minus 2k as we have here. We've still got that plus 9 on the end, so let's do that. And then let's just simplify. K minus 1 squared plus 8 is greater than 0. Now, why do we know that that's guaranteed to be true for all values of k? Well, the reason is that anything squared has to be at least 0, because if you have negative squared, it becomes positive. 0 squared is 0, positive squared is positive. So anything squared has to be at least 0. So what you need to write is just k minus 1 squared is greater or equal to 0 for all k. The magic words here are for all k. And therefore, the k minus 1 squared plus 8, well, that's going to be at least 8, isn't it? Because anything that's at least 0 plus 8 has to be at least 8. So this is going to be greater or equal to 8, which is going to be greater than 0 for all k. And therefore, we've shown that this discriminant here is guaranteed to be greater than 0 for all k. And because this discriminant is guaranteed to be greater than 0, we're guaranteed to have distinct roots for our solutions to this f of x equals 0 for all values of k.